Okay, so we started this course in trigonometry with a review of some concepts from geometry. And so now we're going to officially start trigonometry, and we start by introducing the trig functions. Okay, so in this video, we're going to talk about what are the trig functions. Sine, cosine, tangent, secant, cosecant, cotangent. What are those? What is that? So there's two perspectives of looking at the trig functions. And I think a lot of videos and lectures about the trig functions, they don't really talk about these two perspectives at the same time, which I think makes it confusing. So I want to bring those two perspectives together in this video. Okay, so first, one of the ways that you use trig functions, one of the ways, is if you have any right triangle in any orientation in space, you can use trig functions to get any information you want about that triangle. Angles, side lengths, etc. So let's take a look at a right triangle here. Okay, with a right triangle, you're going to have, obviously, one of the angles is going to be 90 degrees, just one of the angles. And then the other two angles are going to be less than 90 degrees. You can't have a right triangle with a 90-degree angle and then another angle is greater than 90. So you've got a 90-degree angle and two acute angles. And let's call this angle beta and this angle alpha. Okay, now also note that we can orient this triangle any way that we want in space, and it doesn't change the triangle as long as we don't change the size or anything. We can orient it however we want. And here, this has just been reoriented in the plane of the screen here, but you can think about this in full 3D space. And so if your computer screen is like this plane here, so I just moved this triangle to like that, but you could orient it in any plane. You could have a plane that's, this is here's a plane, so you could have the triangle starts off like that. Right, there's beta, there's alpha, and you could reorient it like this. So maybe we started in this plane, and then we've kind of spun it into the page a little bit, and we haven't changed the triangle, though. It's still the exact same triangle. As long as we didn't stretch it or shrink it or change the orientation between the sides, so in other words, change the angles of the triangle, then we can spin it in any 3D way, and it's still the same triangle. Okay, now we've kept this completely general so far. This is any right triangle in 3D space. Every right triangle is going to have a 90-degree angle, and then you're going to have these two acute angles, alpha or beta, and you can make alpha anything you want, beta anything you want, between 0 and 90. And maybe these two are equal, like they might be equal, like there's like 45, 45, 90 right triangles, but in general, these aren't equal. You have a 90-degree angle. So this could be absolutely any right triangle in 3D space. Okay, now we know from geometry that the side that's like across from the 90-degree angle of a right triangle is called the hypotenuse. So we'll label that H. The length of that side is H. And then you also have the two legs, and we'll label those A and B. And these can be a little harder to identify, like depending on the orientation of the triangle, because like here we just go for the hypotenuse, we go straight across from the 90-degree angle, but with like to identify if you've rotated like the triangle and to identify what corresponds to B here, for example, you have to say, okay, the side that's connecting the right angle and the alpha. So here that's connecting the 90-degree angle to the alpha, so that's B. And then here's the 90-degree angle and the beta angle, so this is A. That's how you find the corresponding sides. All right, so now we have this this can represent absolutely any possible right triangle in 3D space. Okay. So now with this, we're going to write out the trig functions. So we're going to say that theta, and this symbol means just like it's like we're defining theta, it's a definition, is any angle within a right triangle other than the 90-degree angle. So pretty much I'm saying theta is either alpha or beta, either one. Any angle within a right triangle other than the 90-degree angle. Okay, so with that, the sine of theta, okay, so the sine of any angle you choose in a right triangle other than the 90-degree angle is equal to the side length opposite of that angle, which we'll just put as O, divided by the hypotenuse. So if we did the sine of beta, then we'd go opposite. That would be B divided by H. The side length B divided by the length of the hypotenuse. That's what the sine of beta means. If we did the sine of alpha, then that would mean that we go the side length opposite of alpha, which is the length A divided by the hypotenuse. Okay? The cosine of theta is equal to adjacent over hypotenuse. And it's kind of confusing with these A's like this. So let me write it this way. I'm going to actually write out the word. And then tangent of theta is equal to opposite over adjacent. So the tangent of alpha would be opposite, the length A, divided by adjacent, the length B. Cosine of beta would be the adjacent, which is A, divided by the hypotenuse H. Cosine of alpha would be the adjacent B, divided by the hypotenuse H. And again, you could look at any right triangle oriented in any way in 3D space and think about, okay, the cosine of alpha is the adjacent side length, this B, divided by the hypotenuse length H. The tangent of beta is the opposite side length, the B length, divided by the adjacent A. Okay? Now, secant, cosecant, and cotangent are just the reciprocals of these three. So it's a little confusing because you would think that cosecant would be the reciprocal of cosine, but it's actually cosecant is going to be the reciprocal of sine. So it's going to be hypotenuse over opposite. You just flip this. All right. Secant theta is 1 over cosine, which is going to be hypotenuse over adjacent. And then cotangent theta is 1 over tangent. Adjacent over opposite. Okay, and so there's the trig functions, and this is one perspective of looking at the definition of the trig functions. We're going to go over the other perspective in a second. But what you're going to see is, as you get further along in school, is that these are really helpful so anytime you're dealing with a right triangle, and you're going to deal with right triangles way more than you think, than you realize. But again, it's oriented anywhere in 3D space in any way. And if you have information about, like, you can plug in the sine of an angle or the cosine of an angle or the tangent of an angle into your calculator. And with that, it's easy if you've got like some information about a right triangle, like some, like one of the angles or like maybe a side length, or, you have some information, then you can use these trig functions to quickly get other side lengths and, and whatnot, to get any information you need about a right triangle. So it's the trig functions and then combined with the Pythagorean theorem. So we know that a squared plus b squared is equal to h squared. So with the trig functions, the Pythagorean theorem, we really have got a full control over right triangles. We can quickly and easily work with them. Okay, now these relations here are just something you're going to have to memorize, and a useful mnemonic is SOHCAHTOA. SOHCAHTOA. The sine is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. And then when it comes to cotangent, well, cotangent's 1 over tangent. That's easy. But then it's confusing the fact that you're going to, in the beginning, I know for me, I think cosecant, that's the inverse of cosine, but it's like the opposite. Just, you got to memorize it. Cosecant is the inverse of not cosine, but sine, and then secant is the inverse of cosine. Not the inverse, like the reciprocal. Okay, now, but this is one perspective of looking at the definition of trig functions. But this isn't complete, and the reason is because if we just stopped here, then all we've addressed is trig functions where the inputs into the trig functions are acute angles, right? Because every right triangle, the angle other than the 90-degree angle, is going to be some angle between 0 and 90. However, with trig functions, as far as like the domain, what thetas you can input any theta, any real number. From negative infinity to infinity, you can input into a trig function. Well, that's technically not totally true, because like if you look, you can see if you divided sine by cosine, you get tangent. And so if like cosine was ever equal to 0, then you'd be dividing tangent, that you'd be dividing by 0, so that's not an input for tangent. But in general, you can think about it like you're definitely not restricted to acute angles with trig functions. So like sine and cosine, you can input all real numbers and there's no issue. So let's talk about, in general, what's the definition of trig functions, the complete definition. Okay, so we're going to start with an XY plane here, and we're going to think about an angle measured from standard position. So we start with here's the initial side, and then we're going to have a terminal side measured in the positive direction to any value theta. So you see theta can be anything, not just an acute angle. It could be 90 degrees, greater than 90, greater than 360. It could be anything. You could have it could be a negative angle. Okay, now once we've got the angle position, then what you do is you think about, you're going to pick a point, any point that's within the terminal position of the angle. So we're not going to, for this case, we're not going to pick a point. We're not going to pick a point over here. No, it's going to be over in the second quadrant, and that point's also going to be in line with the angle. So it's any point like on this line. It could be way out here. It could be here, but like it's in line with the terminal position of the angle. So we're going to pick this point, but we could have picked this point and extended the arrow, or we could have shrunken the arrow in and picked this point. Okay, now this point has position x, y, this point P. Next, what we're going to do is we're going to create a right triangle to where the right angle is connected with the x-axis. So this is the x-axis, x, y. So we could do this to create a right triangle, but then the right angle would be connected with the y-axis. We're always going to do it to where the right angle is connected with the x-axis. So even if we had a point like down here, this would be the right triangle. If we were out here, this would be the right triangle. And in these cases, this is the angle theta, and this is the angle theta. What we're thinking about is what's like the sine of this angle? What's the cosine of this angle? It's this greater than 90-degree angle. In those cases, that would be like greater than, this angle would be something like, 2 280, 290 or something. What's the sine of 290 degrees? That's what we're thinking about here. Okay, but just looking at this, this right triangle here has the side lengths are, well, this is y, and this is x. Now, this is a little bit different because, so in this case, y is positive, but x is a negative value, right? We're in the negative x. And then this is r. R is the square root of x squared plus y squared. And just remember, r just depends on the point you picked. You know, if you picked a point out here, you can have a different r, but it's still related to the x and y the same way. Okay, so what you do is you say that the sine of theta, in this case, you still come to this right triangle, and you think about opposite over hypotenuse, right? SOHCAHTOA, sine is opposite over hypotenuse. You come to the angle that's made with the origin. You come to this angle, okay? So you got two angles to choose from in this right triangle that you've created, but we're going to come to always come to the angle that's with the origin. And then you do the same thing. You say opposite over hypotenuse. So sine of theta is y over r. Cosine theta is adjacent over hypotenuse, x over r. But notice, in this case, the cosine of theta is going to be negative, right? If we come back, here, there was no scenario where we could get a sine theta, cosine theta, tangent theta that was negative. Why not? Because you can't have a negative side length of a triangle. There's no such thing as a negative side length of a triangle. And all of this, every one of these definitions was based on you're dividing one side length by another side length. That's always positive. Okay, but we can see with the general definition of trig functions, you can't have a trig function of an angle, like the sine of an angle or the cosine of an angle, be negative. Okay, so the tangent of theta would also be negative because you'd have opposite over adjacent. All right, then the cosecant of theta, that's the reciprocal of sine, is r over y. The secant theta is r over x, and the cotangent of theta is x over y. Okay, so now here is the complete definition of trig functions. You can see with this, you can think about the sine, cosine, tangent, cosecant, secant, cotangent of any angle from 0 to 360 degrees, but, you know, or negative angles, anything. So you think, okay, let's think about the angle 210 degrees, which is the same thing as negative 150, I believe. So you draw an XY plane. Then so 210 is 30 degrees greater than 180. So we're, you know, somewhere here. So we're going to pick any point that's in the same quadrant as where that angle terminates, any point along the termination line. So, okay, there's about 45 past 180, so let's say that's about 30. Okay, so we're thinking about, we want to evaluate the trig functions for theta is equal to 210 degrees. So we picked this point here. You could pick any point as long as it's along this line, this termination line of the angle. It can't be off the line. That point's going to have a distance from the origin, r. So it just depends on the point we pick what r is going to be. Then from here we create a right triangle to where the right angle is connected to the horizontal axis, or the x-axis. So this distance is y, this distance is x. But you think about these in terms of the coordinate system. So this x value is negative and this y value is negative. Right? This is the negative y direction, the negative x direction. So then what you do is to think about the trig functions of this angle, you come to this angle here. You come to this angle of the right triangle, the one has vertex at the origin. and then you use the SOHCAHTOA mnemonic. The only difference is that the y could be negative or positive. The x could be negative or positive. The r is always going to be positive, right? So sine of theta is y over r, but that's going to be negative in this case. In this case, it was positive. Cosine adjacent over hypotenuse is going to be negative because x is negative, r is positive, r is always positive. Okay, now you might be wondering, how can we just pick any point? Wouldn't it, if the r is different, wouldn't that change the trig function values? No, it wouldn't, because remember, we can't go off of the terminal line. We have to stay on the terminal line. So what happens is, no matter what the resulting right triangle, based on the point that we pick, the r that we end up with, any possible right triangle that we end up with, they're all going to be similar. Why? Because the angles, they're always going to be right triangles, and you're never going to change this angle because we're staying on this line. So that means this angle is unchanged. It's similar triangles. And as we know with similar triangles, the lengths of the sides can change, but the proportions of the corresponding side lengths don't change. And that's what trig functions are based on, the proportions of the side lengths. Okay, if we come back here, just to point this out, so we had talked about how we could reorient this in all of 3D space, and as long as we didn't change the size of the triangle, we wouldn't change any of the trig function values, right? However, we could change the size and just scale it up or down without changing the angles, and the trig function values wouldn't change, right? Because if you don't change the angles, then the triangles are similar, right? So similar triangles are going to have the exact same values of the trig functions. Okay, now some other questions you might be asking yourself are, well, if the radius doesn't matter, so in other words, if the point that we choose along this line doesn't matter, why don't we choose something like a radius equal to 1? And you're right, a radius equal to 1 would make things much simpler. If you look at all of these trig functions, if you make the radius equal to 1, then sine theta is equal to y, cosine theta is equal to x, etc. And that's exactly what is done with the unit circle, which we're going to discuss in a later chapter. But the unit circle is the standard form of what's used to define trig functions. It's a unit circle because the radius of the circle is equal to 1. So you travel around a circle with r equal to 1, and you use that to define all of the trig functions. But technically, you don't have to use a unit circle. More generally, you can use a circle of any radius, like we showed here. You also might be wondering, why are trig functions defined so that when you input certain angles, you get negative values? So trig functions are just a definition. We can define this however we want. Humans define this. So why isn't it defined to where, let's say this angle theta is 135 degrees. That means that this is 45 degrees. So if this is 45 degrees, why isn't it defined to where if we take the cosine of 45 degrees, we get a positive value, but if we take the cosine of 135 degrees, which is this direction here, well, since that's also 45 degrees and we pretty much have the same right triangle in both situations, why isn't the cosine of 45 and the cosine of 135 the same value? Why do we have it to where the cosine of 135 is negative? Well, an example I can give you that will illustrate why defining it this way is useful is, so imagine this is a direction of motion of something. This is like a velocity. So velocities have a magnitude and a direction. And this is some object. Okay, now imagine this is a force vector acting on that object. Forces also have a magnitude and a direction. So these arrows have a size and a direction. Well, at some point, you're probably going to learn about something called the dot product. To calculate the dot product between two vectors, you take the magnitude of one of the vectors, multiply that times the magnitude of the other vector, and then multiply that times the cosine of the angle between the two vectors. What that ends up meaning is that you're multiplying this vector, the magnitude of this vector, times the projection of the magnitude of this vector in this direction. So not this entire vector, just the percentage of this force vector that's pulling in the same direction as this motion. Okay, so now what if we had a force that was directed in this direction? Let's say this force is the exact same magnitude, size as this force, and the angle between this force and the horizontal, theta, is the exact same angle as the force, this force between the horizontal. So both of these are theta, same angle. Well, if you took the dot product between this force and this direction, what that means is you would project this force onto this direction, and then you would multiply that by the magnitude of like the velocity. Well, these are the exact same force magnitudes, and they're at the exact same angle from the horizontal. So you're multiplying the exact same force magnitude by the exact same direction magnitude. So you're going to get the exact same value. However, there's a difference here, right? This force is pulling in the opposite direction as the direction of motion of the particle. This force is pulling in the same direction. So you would want these values to be different. What you would want is you would want this dot product to be negative and this dot product to be positive. And that's exactly what happens when trig functions are defined this way. This force is going to be pulling in the negative direction. So you're going to have that's why the cosine of this theta is going to result in a positive. But if you had the cosine of this angle here, because that would be the angle of this vector, that's going to end up being the exact same magnitude as this, the cosine of this, but just in the negative direction. So again, that's why it's very useful to define trig functions this way, to where you can have negative values. Okay. And the last thing you might be wondering about is, how does this right triangle definition of trig functions relate to this standard definition, this more full definition? Well, okay, here's the right triangle. Remember that these two angles, the two angles that aren't 90 degrees in a right triangle, are always going to be acute angles. So based on the standard definition, you're always going to be dealing with an angle that's in the first quadrant. And therefore, the x and the y are always going to be positive, which makes sense. Because here, you're dealing with the side lengths of a triangle, which are never negative. Now, if we rotate the right triangle, we can put alpha in standard position and see how the trig functions of alpha are directly related to the side lengths of the triangle. Sine of alpha is opposite over hypotenuse. Tangent of alpha is opposite over adjacent. The trig functions are always positive. But what about beta? There's no way we can rotate this triangle to get beta into a standard position. However, to illustrate how beta is just like any other acute angle on this diagram, it's just a matter of perspective. So, for example, let's make this a 30, 60, 90 right triangle. We're going to learn later that a 30, 60, 90 triangle will have side lengths proportional to the hypotenuse being 2, the side between the hypotenuse and the 30-degree angle being root 3, and the side between the hypotenuse and the 60-degree angle being 1. The side lengths of any 30, 60, 90 right triangle will be some proportion of these numbers. But what you can see is that we could switch these angles. When we switch the angles, we want to switch these side lengths, with the hypotenuse staying the same. So now we can use either one of these triangles to put the 30-degree angle into standard position or the 60-degree angle into standard position. There you go. Sine of 60 is opposite over hypotenuse. Cosine of 60 is adjacent over hypotenuse. Tangent of 60 is opposite over adjacent. And once again, there's the 30-degree angle in standard position. So any angle within a right triangle other than the 90-degree angle is just an acute angle on this standard definition of trig functions layout.